Thank you for being part of this study. We're here studying about linear vector spaces. We have this divided up into three different parts. People said they wanted a shorter video broken up, so this is going to be divided up into three parts for lecture number 9. This is part number 1, linear combination. We're dealing with linear functions and linear operations. When we deal with part 2, we will be going into linear dependencies and independencies. Then we're going to go over the last part that we will go over. It'll be linear vector spaces. Okay, so those are the three areas that we'll be looking at in lecture number 9. So far, we've covered a lot of things in matrix, a lot of things in different variables. And so as we go through, we want to get a clarity on what is vectors, what type of vectors actually are linear, what are linear functions, what are linear operations. So, as we try to define range and domain of vectors, we're doing vector transformations. Usually we have a domain where we have x, which is what's in here, and these variables here. And then we have it going over to a codomain or to a range. It's referred to also the codomain output of the function, which is the entire function. With vectors, they have many dimensions. We usually work with 2 dimensions, and now we're working with 3 dimensions. And when we work with time, we work with a 4th dimension, and we can go all the way up to n different dimensions. And they all are dealing with real numbers, as you can see here. We're dealing with real numbers. Okay? And they will go to the power of n, and over here you can have more solutions. That's where the y falls in, and they're also real numbers. When we talk about mapping and when we talk about linear algebra, linear functions, linear operations, what we like to do is we like to have it in 3D, as you can see here. And then in a practical world or with our settings, we can transform it from 3-dimensional into 2-dimensional space. Okay, as you can see here. So this is x, y, z, and this is x and y. And you'll see that we'll be doing many different types of transformation. When we talk about linear transformation, a vector, which can be called 3a minus 4b, is called a linear combination of a and b, because you're doing multiplication of a and b, and you're doing some adding and subtraction to a and b. And so when you do that, you are combining different linear vectors. And as you are as you're using these different vectors, there's many operations that can be used and that are used. Okay? Usually there is a constant in front, A or B. I put in 3 here so that we can have some type of idea. We also find out that all linear combinations of A and B lie in the plane, in a plane where A and B are located. Now, when you do transformations, they have to follow certain rules. The 2 rules that we'll be talking about is the addition rule of what you do inside of that domain, that you can separate them and they'll still add up to be the same, or you can multiply a constant on the inside and you can bring it outside, and that's scalar. Now, when you connect one vector to another, you connect the tail, and then you connect the tail to the head of the other one, and that's how you add them. And if you subtract them, it goes the other way. And so we'll be looking at different types of functions that can operate in this world. So, are square roots linear? No. Square roots are not linear. Are matrix operations, are they linear transformations? Yes, they are linear transformations, and we will be using lots of linear transformations as it relates to matrices. Orthogonal transformation preserves the length of the vector, so the vector stays the same size. Okay? The inverse of an orthogonal matrix equals its transpose matrix. Okay? So you have the inverse is equal to the transpose. Now, when you multiply these two together, the inverse and the transpose, guess what you get? You get the identity matrix. Okay, so this is very powerful tools that we'll be using. We're also going to find out that the determinant of a matrix that is orthogonal, that its determinant is either a plus or minus 1. Okay? Well, remember, we already said if we multiply them, it'll give us identity. Okay? And so what we'll find out, if it's a plus 1, then it'll be a rotation. It will be rotating the vector. Okay? And if it's a minus 1, it'll be a reflection. And we're going to go over those and give some examples in reference to that. Okay, when we're looking here at matrix, the form that we usually have it in is an equation, okay, like this, 2x minus y, 3x plus 4y. So this form, and then you have a matrix multiplied times a vector. So this is our matrix out here. This is our vector. Our A here is our matrix, and X here is our vector. Here, right here is our matrix, and here is our vector. And as you can see here, like if we're looking at this particular point, or this particular vector, 1, 1, we go over 1 on the X, and we go up 1 on the Y, and that's that point. Then if we take this and we multiply it times a different one, and we have a matrix times a vector, we see that this is 1, 7. So we'll still go over that 1 in the X, and we'll go up 7. Okay, when we talk about rotation, okay, there's specific types of transformation matrices that we'll be dealing with. The first one we would like to talk about is the rotation. It rotates around the axis. And you'll be able to rotate it if you use the sine and the cosine. Okay, as you can see here, across the diagonal, we have the cosine, and across the minor diagonal, we have the a plus and a minus sign. Now we want to also talk about not just rotating of the axes, but also of the vector. Okay, when we rotate the vector versus rotate the axis, as you can see, the only change that we still have cosine, sine, cosine, sine, cosine, sine. The only difference is that the sign on the sine is in the first column versus it is the sign on the first row. Okay, that's where the big difference is. And like I said, we're going to go over some examples. We're going to go over a example and then have you follow up and do an example also. Okay, here we have, if we want to rotate it 45 degrees, and so if we're going to rotate it 45 degrees, we're going to have to, 45 degrees is going to give us 1 over the square root of 2. Okay, so with your 45 degree that you'll be using, you'll have to, you'll plug it in to this equation. Okay, and as you can see, if you use 45 degrees, as you have here, this shows how you would transform this. And this is how this would turn into this particular vector. But you would be multiplying this here, this matrix, with its determinant, times our x. And this is what we're calling a transformation. We're moving and transforming the plane or the vector that we're using. What happens at 90 degrees? Okay, 90 degrees, we do the same thing. Okay, right here at 90 degrees, we're able to plug in 90 degrees. We know 90 degrees will be, if it's a cosine of 90 degrees, as you can see here, it'll be 0, each of the cosines. And then the sines will be a 1 and a negative 1. Okay, so as you can see, there's no square root rotated, multiplied here, just as we did have the 1 over the square root of 2 for 45 degrees. And as you can see here, we can rotate this. Okay, we can change as we say, to rotate the vector from this position over to this position. And as we go through this, you'll be able to see. So as you can see here, we have a 90 degrees. Okay, this is our original x. It's where x at 2, 1, 2, and y at 0. So this is our first point. This is where we start. Okay, and then we rotate it 45 degrees, and that's what gives us this answer here, the square root of 2. As you can see, it moves from here over to the square root of 2 over 2. So the square root of 2x and then the square root of 2y, and that gives you this point. Then we rotate it from its original to 90 degrees. Okay, we find out that we have a 0 in the x, as it says here, and you have 2 on the y-axis. Okay, so that's how we're able to rotate them. If a vector is subject to a sequence of transformation, just like we just did a sequence of transformation, 45 degrees, 90 degrees, okay? If it is subject to a sequence of transformation, we use matrix multiplication. And we want to go from, in the order, from right to left. Okay, when we look at this, we're going to use an example because we just went through one. So what we want to do is we want to have a reflect the vector 2, 3 across the x-axis. Okay, so we want to change it and move it over to the x-axis. That's what we want to, and then we want to rotate it by 90 degrees around the axes. Okay, so let's see how we would do that. Okay, so the first thing we are going to look at is, okay, we have a 2, 3. And so what we want to be able to do with our 2, 3, we want to first be able to rotate it around the x-axis. So the question is, what does that give us? Okay, if we're at 2, 3, we're going to make a change. Remember the order, continuing on with the question, identifying the problem. When we go back and look at our, what did we say? We wanted to rotate this after we moved it 90 degrees. Okay, when we move this here, we are going to multiply. This is our vector, this is our matrix, and this is our transformation that we'll be using on it. And remember, this was cosine of 90 degrees is 0, cosine 90 degrees is 0, sine minus sine, that's a -1, and sine. Okay, so this is the one that you'll be multiplying this time. Now this was the answer that we got on the last page. Let's see if we can go back. So you can see it. Okay. All right. This is what we have. Okay. All we did was take the reflection from 2, 3, and now it's going to be rotated on the axis of the y-axis. So what happens is that this moves from 2, 3 to, we're changing, the 2 will stay the same, we're still going to move the same distance on the x-axis, but we're now going to flip it on the around the x-axis and put it in the y-axis, so the y will turn to negative. This would be 2, -3, and when you multiply this, that's what you get. So right here you have, this is representing the negative y. Okay, so we're going to use this specific matrix to be plugged into with the other ones. Okay, so you can see that this is that matrix, and this is the new one. This is the one that's the 90 degrees. So this is our new m. This is our x, which is still 2, 2, 2/3. Then we're transforming it with a 90 degrees matrix. And when we multiply that, we get this specific matrix. We multiply this matrix times our x, and it'll give us our x prime. What is our x prime? Our x prime is this new transformed matrix. And so if we multiply this out, we see that this is what? 3. Okay. You multiply this to 0, and the 3 against the 1. So this lets us know that this is 3. And then this is 1 against 2. This is 2, and 0 against 3. So our new dimension is going to be 3, 2. Okay, so now we was able to show you how we were able to rotate it around an axis. We showed you how to move it rotating around 90 degrees around another axis. Now we're going to talk about we're going to give you a practice problem, but we're going to have you do it in the third dimension. Okay, so we have the matrix representation, a rotation around the z-axis, okay, in 3D. Now, if you notice here, the only thing that we added was, guess what? A 1 there. That's all that was added. Okay, everything else is 0. These were the same. And so when you solve this problem, you'll be solving it the same way that we did. So first we want you to do is what? Okay, so this is the reflection through the XY coordinate. Find the matrix that represents a rotation of 45 degrees. Okay, we did show you about the 45 degree if you want to go back and look at it. About the z-axis, followed by a reflection through the XY plane. Remember, all you need is 2 vectors, and they make up the plane. Okay, remember that. Okay, then apply the transformation to the vector I, J, K. Okay, so I believe this will be our this is our first break that we're having. Thank you, and we'll look forward to you doing part 2.